In this lesson, we're going to go ahead and continue our discussion about atomic theory and continue on from the ideals we've talked about previously, such as Dalton and his journey to find a pattern in a periodic table. So in this lesson, you're going to have two handouts, the first of which is going to include questions that are fill in the blank using your scientific concepts to fill in the blanks. You're going to have to use concepts and inquiry to think for yourself and come up with an idea to solve a problem that's more abstract. And then later on, you will also be making your own orbital diagrams. If you're asking what this lesson does for you or how are you going to use it in the future, we want you to understand that when we use models in atomic theory, we use them to visualize the interiors and the makeups of these structures. This helps you predict the interactions of matter, and it also helps you understand how the world works, how the world is made up, and how you are made. This also is a good lesson to help you understand how we got to this point and got to these concepts and theories, and how it started out with people like Dalton. Because in the portion of the lesson in which you'll be making your own models, you're going to be using scientific inquiry from the concepts that you've learned to pattern just as he did. He, at one point, laid out all the elements that he knew, which was far fewer than ours, with all the information that he knew about them, and he was trying to find a pattern, the best way to make a good table. And without his work, we wouldn't have the current periodic table that we have now. So this will help you learn by inquiry. This will be a student-driven lesson in which you will be working in groups and interacting with each other. You'll have interaction and inductive learning, and this is the best way for you to learn these lessons. You will be assessed on 2 points. Firstly, you will be assessed on your scientific knowledge through the concepts that have been given and your ability to answer questions correctly. Secondly, you will be assessed on your orbital diagrams, your ability to think outside of the box and form these diagrams correctly based on the knowledge you have and the ability to see and sort out patterns. All right, so what we need to do is we're going to start talking about the periodic table, and we're going to talk about atoms. And this is going to be an important lesson to pay attention to. Some things that would have been taken care of in a prerequisite lesson would have been basic atomic theory and its history, talking about Dalton. We would have talked about matter, and we would have talked about its interactions. We would have talked about the metric system and different things of that sort. Now, in this lesson, you're going to be getting a greater understanding for how chemicals are represented, their symbols and what they're made of, and then more into atomic theory. We're going to be talking about how atoms of different elements differ, what makes them different, what makes them unique, and their makeup as well as their function. We also will be talking about isotopes and atomic weight and important parts of atomic theory. An element is a pure substance that can't be broken down into simpler substances. So for instance, hydrogen and oxygen are elements and they can't be broken down into simpler elements or simpler things. This is important when you talk about things like alchemy in history. It actually explains why alchemists could not change anything into gold, even though sometimes they claim they could, and some people still believe that you can do that. This basic understanding is why you actually can't, and we'll talk more about that later. There are over 100 elements, and 90 of them we have found to be naturally occurring in the universe. We believe these elements to be universal. More than 20 of them we've made artificially or synthesized in the lab, and this is done through particle accelerators and other types of chemistry that we won't be able to get into here. But you've potentially heard of some elements such as iron and carbon. You've probably never heard of rhodium before, and that's okay. Some elements have been around so long that we symbolize them through use of their old Latin names. Sodium we've known about for quite a long time. And in Latin, it was referred to as natrium. So we use the first two letters, but most symbols are based on their current names or some kind of a system like that. So it becomes pretty easy to learn the names with their symbols. In your chemistry career, it's going to be helpful to know about 10 to 20 of them. And we'll kind of go over what those ones are later, but it's going to be, these are going to be some of them. As you can see from this list, there are some important ones to know. Again, these four, carbon, hydrogen, oxygen, and nitrogen, are the four most basic elements to life as we know it, especially carbon. These elements are going to be part of a class of chemistry we call organic chemistry. And again, anything that's organic or organism or living are going to have to do with these elements. Some of these you've heard of, some of you haven't, but what's really interesting here is when you look at something like arsenic, you think deadly, skull and crossbones, but it's actually something that exists naturally in the human body and has a function and can be helpful. What you should gain from this list is that many times the idea of poison doesn't have to do with its name or what its chemical composition is, but very often it has to do with dosage. Here, you're going to be going to the dynamic periodic table, and this is going to be very helpful for you down the road. This table will help you to understand each element and how it's made up. It has a huge amount of information available to you, and I invite you to use this throughout the years of your training in chemistry. Now, atomic theory is not quite this simple, but if we had to narrow down the four biggest highlights, this is going to be it. You need to understand that matter, all matter, everything that exists in physical nature is composed of what we call atoms, the smallest whole part of matter. Any atom within an element, so all atoms in all hydrogen atoms differ from all carbon atoms. No two atoms of different elements are the same. Chemical compounds consist of atoms in different ratios. So if you have a compound of hydrogen and oxygen together, such as water, you're going to have a ratio of 2 to 1. Now, what we would have gone over before as a prerequisite is an understanding that when you have a chemical reaction, matter is conserved and you don't lose atoms of any particular element. When a chemical reaction occurs, all that happens is that you are rearranging those atoms. Atoms are composed of small particles that are called subatomic particles, or SAPs. These are protons, neutrons, and electrons. Now, protons and neutrons contribute to the mass of an atom, but electrons are so small, so insignificant that they don't really contribute to the mass at all. But they are still important. So the masses of atoms and their constituent subatomic particles are very, very, very small. It's a small amount of mass, but it's still there. Protons and electrons both have a charge. They're different charges, but it's the same amount. So protons, we usually say, have a positive charge, and electrons have a negative charge. It's the same amount of charge as a proton, but it's just a different sign. Okay, so they cancel each other out, and that's very important. Neutrons, as the name seems to suggest, being neutral, have no charge at all. Excuse me. Now, protons and neutrons are packed very, very tightly close together in a little area we call the nucleus, or the center of an atom. The electrons don't want to be anywhere near that nucleus, so they circle and orbit the nucleus at a relatively great distance. If you were to imagine a P representing the nucleus of an atom in the stadium, and the stadium itself representing an atom, that's how small and compact the nucleus is within an atom. So you'd have a P in the center representing the nucleus, which contains the protons and neutrons. The electrons would be orbiting and circling that P somewhere on the outside of the stadium at a great distance. Now, some designations you need to know are the atomic number, which we designate with the letter Z. That is the number of protons in each element, and every element is different. That's how we organize the periodic table and how we organize elements, by their proton number. So, all hydrogens, no matter where you find them or how you find them, all hydrogens have one proton. They have the same atomic number. Now, we like to say that atoms are neutral in their charge. This is necessary, and this happens because all atoms have the same amount of protons and electrons, generally speaking anyway, and this makes their charge equal. This is their happy, nice living state where they like to be. You can change the electron number, but they do not like that. This is not the best state of atoms, and they like to keep a neutral charge. The mass number we represent with the letter A is the number of protons plus the number of neutrons in an atom. This is important because we have something called an isotope. An isotope is a particular element that has different mass numbers. So what I mean by that is that we're not changing the atomic number, because that's protons. If we change how many protons a carbon atom has, well, it's not carbon anymore. But if you remember, the mass number is protons and neutrons. So if we change the neutrons in a carbon atom, we become an isotope of carbon. Carbon-12 is the most common. That makes up pretty much everything. It's about 99%. But if you've ever heard about chemical dating, carbon dating, you've probably heard of carbon-13 and 14. Now what happens is we take the mass numbers for these isotopes. There's only 3 isotopes of carbon, and so we take the 3 mass numbers and we average them, and that gives us the atomic weight, the average. And so out of all carbon atoms in the universe, this is going to be the average atomic weight. Now you need to go and watch a video that'll help you understand this a little bit more. And once you do that, you'll have a quick quiz. Now, if you think back to earlier, you'll understand the answer to this question on your think sheet. People used to believe and think that you could turn a piece of lead, or other objects for that matter, into gold. Well, why isn't that possible? When you look at your periodic table, what makes them different? How many protons does gold have? How many protons does lead have? Because lead doesn't contain gold at all, it can never be gold. Now, with that being said, we actually can turn lead today into gold through nuclear physics and nuclear chemistry, but it's a difficult process in which we basically aim a powerful particle accelerator at lead, and we add or subtract the amount of protons from an element to turn it into another element. So if you can take lead and give it the amount of protons that is necessary to be gold, then it does become gold because it has the right amount of protons. It's a very expensive process. You actually lose money in doing so, so it's not really a money-making scheme. It's just a cool thing that we can do. Now you need to take out your Skittles and get ready for that activity. You're going to be making your own atoms by practicing the amount of protons, neutrons, and electrons in an atom. You're going to start out with hydrogen, and this is where you're going to need to use your periodic table that I gave you access to. You need to remember, if you need to determine the number of neutrons in an atom, all you have to do is subtract the number of protons in that atom from the atomic mass. And this is all the information that you need. All that information is very accessible on your periodic table. Good luck to you, and make sure to turn in your thanks sheets and to show your instructor your various atoms. So far, you've learned that there are 3 subatomic particles: protons, neutrons, and electrons. So now that you're ready to do your orbital diagrams, I suggest taking out your Skittles. And I want you to separate them into the different colors. I suggest that you use the 3 most numerous colors to represent your subatomic particles, and the smallest of those to be your neutrons, because generally you don't need too many neutrons in these orbital diagrams. So for me, I have my colors separated out already. Your first assignment was to look at the element of hydrogen. If you look at hydrogen, it has an atomic number of 1. So that means that we're going to have 1 proton. So I'm just going to pick out what I have for protons, and that's going to go in the nucleus, like we've discussed before. Now, for every proton, because it has a positive charge, and in order to negate that charge or to balance it out, you're going to have an equal number of electrons. So if we have 1 proton, we're going to have 1 electron. Now, if you remember, the rule with your orbital diagrams is that electrons must fill the smallest orbitals first before you can go out to the other one. So that can go either here or the other spot. It cannot go out here to what we call in higher energy. Now, what about neutrons? Well, if you remember from the lesson, the way we get to that is we take the atomic weight, which in this case, if you look at the little box on your periodic table for hydrogen, it'll say 1.0076, something like that. So generally, we just round to the nearest whole number, so that being 1. And then we subtract the atomic number from that. So 1 minus 1 gives us 0. There are no protons in a hydrogen atom. So if this is something close to what you did great. Now let's move on to helium. Helium has an atomic number of 2. So we're going to get 2 of our protons. As I said, for every proton, you need an equal number of electrons. And as said before, you must fill the lower orbitals first. Now, our atomic mass for helium is 4.0 something. So we're going to round to 4. 4 minus 2 equals 2. So I'm just going to pick another color for that. And we're going to have 2 protons in our nucleus and 2 neutrons. Okay. Now, how does that look? Have I obeyed all the rules? Yes. Do I have the correct amount of electrons, protons, and electrons? I'm sorry, protons, electrons, and neutrons. Yes, I do. Let's do one more. I am a big fan of organic chemistry. So the most important
molecule, oh, I'm sorry, the most important atom we look at that is carbon. Carbon has an atomic number of 6. So that means we need lots of little protons in here. I might have picked a bad example because this is going to take up a lot of room. Okay. And if we have to, we'll start at a different orbital if we don't have room. Now, the atomic mass is 12. So 12 minus 6 is 6. 1, 2. All right. So that means we need 6 neutrons. And try not to eat these like I've been doing during your lesson. That will come later as the reward. And you don't have to do it nice. Just try to get them in there as best you can. Just as best you can. All right. 1, 2, 3, 4. Okay. So, if we have 6 protons, we also need... That's okay. I messed up my colors, but that's okay. We also need 6 electrons. So we need to fill the smallest orbitals first. 2 here. And then generally, what you'll find out is we kind of do it in terms of pairs. But however you want to do it is fine. Yeah, I think we're going to do it in terms of pairs. All right. We have 6 electrons, 6 protons, and we got 6 neutrons. Now, if you remember to your lesson, we also had the discussion of isotopes. So how could you change this to be carbon 12, carbon 13, carbon 14? Now, let's have an even bigger discussion. This is where you need to understand what it's like to be Charles Dalton, as we talked about. What has been the pattern here? As we look at the periodic table from left to right, top to bottom, what has been the pattern? The pattern, hopefully you've seen, is that we are growing one at a time in the number of protons. This is what Dalton saw when he did the same thing that you're doing. He would take each element that he knew of at the time and arrange them on a table with all the information that he knew about them. And eventually he finally saw a pattern that what really defines each individual element is their protons. And he decided that the best way to organize a table was to order them in terms of the number of protons. So we currently have about 118 elements on the periodic table. The 118th is oganesson, and it has 118 protons. Okay, and so that means it has 118 electrons. Now, its weight is approximately 294. So how many electrons would we need? Obviously, we need way too many subatomic particles to fit on this, but we would have to have 176 neutrons to build that orbital diagram. So, if we were to be the future scientist, tomorrow's scientist, if you were to try to discover or synthesize the next element on the table, what would you have to do? Well, we know that the next number up would have to be 119 protons, right? Now, there's no real way to know its exact weight, but generally the weight increases only by a little bit, by 1, 2, or 3, or just a few. So if we were to guess, maybe we could say it was 296. So 296 is the atomic weight. The atomic number is 119. That means that you would need 177 protons and 119 electrons to work. So I want you to think about this and think about how this might be done. You can also think about the pattern here and why it's important. If you understand these structures, you can understand how matter interacts with each other and how you personally are made. I want you to go ahead and try a few on your own, pick at least 5, and then when you're done and you've turned them in to your instructor, then you can go ahead and eat your Skittles. Hope you enjoy.